Hi, welcome. So today we're going to do exam 1 review, and then on Thursday we're going to start a new topic which will be continued on after the exam, and that will be op-amps. And so this Thursday is going to be your last homework for the exam 1 topics. So exam 1 will be next Tuesday. Put that in there. So it will be during our normal time here, 3:40 to 5 p.m. It will be in the Engman Lab, which is the Warnock Engineering Building, L210. So it will be open notes, open book, open computer. So it will be like your Canvas quizzes where you will solve the solution. Is that a good or a bad thing? That's a good reaction or a bad reaction? Okay. So you'll be asked to solve the problem. You may be asked to combine a couple of solutions. If you get it correct, it will give you automatically like, yes, you got that correct. If you didn't get it correct, we'll get partial grading. So make sure that you bring, so if you want to take it on your own computer, you feel free to bring in your laptop. During the exam, I ask everyone to keep open all of their windows on the desktop so that you can see every single window. So there shouldn't be extra tabs in there. So if you have the book, make it small. If you have an online calculator, you put it here. Here's your exam. Whatever else you want. You can have them all on the same screen. As I walk by, I just need to make sure that I am able to see exactly what you're doing. As I said, it is online calculator, so you're welcome to use those if you, okay, so open notes, open book, open computer, bring whatever it is where you upload, if it's been your phone, if it's been a tablet. You're welcome to still work on your tablet if you like to do that and then submit it on your tablet. That's fine to do too. So just bring whatever device you use to upload your work. So you will scan it in and have an option to upload your work just like you have for the quizzes. So it will be kind of a similar format that you've seen in the questions like the quizzes. It will just be more of them. So you do need to be very efficient. Typically you'll run out of time if you are having to look for like, oh, how do I solve this? How do I solve this? How do I solve this? If you're able to like, oh, I see the problem, I know exactly what I need to do, you can even go have time to recheck. That's kind of at the level that you want to be for the exam. So lots and lots of practice. All right, topics. Well, before I move on to topics, any questions about the format and what that's going to look like for the exam 1? Yes?
If you're allowing a calculator on a computer, can we just bring our own?
Yeah.
Okay.
Yeah, you're welcome to use your own, but a lot of people are like, can I use an online one? And if you use an online one, that's also okay to use. A lot of your other classes may not have allowed that in the past. So I usually state that one because usually you can, well, some don't. Math doesn't usually let you use your calculators. But in here, yes, you can use calculators. You can use online. If you use the online calculator, I suggest you take a screenshot of it and include that in your work that you're submitting so that if you did an error in punching in the number and you have it written on your page correctly, then that will give you extra points. But if it's like, well, I have no idea what you did because I can't see what you did and where the error is, you'll get those points marked off. So as much information as you can include usually means that you'll get more partial points. Yes.
So for that, should we then, if we're not using an online calculator, should we take a picture or scan our physical calculator?
You can.
Okay.
If that's, make sure it's an easy process if you are going to do that so you're not spending the whole time trying to capture all your information. I mean, the main focus is to test you on the content, not can you really figure out how to scan these things. So yeah, if you do it, just make sure it's efficient and it's an easy process to add. All right, any other questions, comments? Yes.
Do you know about how many questions it's gonna be?
2, 3, 4, 5, 6, 7, 8-ish, 9, 8 to 9. Some of them may be pretty quick questions. 10, 6. Yeah, they'll probably be, if there are 10 of them, that will be quicker questions. If there are 5 of them, then it might be a combination questions to ask you a couple questions within there, and then sum up the numbers of these, which one was maybe a voltage divider, one was a current divider, so that I can get a number in there. Those would be kind of a combined question. So the topics itself, KCL, which is Kirchhoff's current law, Kirchhoff's voltage law, Ohm's law, I had these down here so I didn't forget any of them. Power, equivalent resistance, current dividers, voltage dividers, the Wheatstone bridge. So with the bridge, I wouldn't ask you derive this whole equation. I may ask you a concept question on that one, which would be kind of a quick understanding, trying to think of an example, really quick one. Giving you values for R1, R2, and R3, and say, okay, you measured R4 to be this. Do you expect the voltage VAB to be higher or lower? So that would be an idea of a concept question. You would need to understand that, and you would need to understand it's a bridge, and if this divider is different than this, what impact does that have? If the value is VAB is 0 in between the Wheatstone bridge, and R1, R2, and R3 are these values, what value would R4 be? So those would be kind of some example questions that I could ask for the Wheatstone bridge. I won't ask you for a derivation for that one. You did that in the homework instead. All right, Thevenin equivalent, the ending, yeah. Thevenin equivalent. And I like to focus on Thevenin, so I'm going to test you on Thevenin, so don't worry about the Norton for that. Just make sure you're really good at the Thevenin. And then max power transfer. So these will be all of your topics that you could expect to be within either a problem themselves or within a problem. For example, KCL and KVL could also be tested when you're doing Thevenin equivalents or voltage dividers or current dividers. So that kind of a question could be in there too. All right, questions about upcoming exam 1. So again, next Tuesday, 3:40 to 5. Yes.
Is there gonna be superposition?
Oh, I totally forgot superposition. Thank you. Yes, superposition will be on there too. Yes.
Is there a review or a practice exam?
So for the practice, the best way is to utilize the Unit 1 practice problems. And now they have an example one for every single problem on there. It won't have kind of these concept questions that I just mentioned about the Wheatstone bridge, but it has an example kind of problem that you could kind of see for each of the other ones. And then when you refresh it, it hopefully should give you a new problem. So there should be unique problems in there. All right, any other questions? Yes.
Would we expect to derive the Norton equation from the Thevenin, or just
Understand it,
okay?
but I will not ask it.
Okay.
So focus on Thevenin because I like Thevenin. So make sure you can derive the Thevenin one. Okay, yes.
Are the like answers for the Unit 1 practice problems correct? Like if
They should be. So all that I have gotten, I have corrected as far as all the errors that were there. And so as far as I know, they have all been caught, but I won't guarantee 100%. So if you're still like, I know I'm doing this right, or I think I'm doing that right, just please reach out to me and I'll try to respond pretty quickly. All right. Other questions? So as you guys saw, I had a request to do the homework different this time because there were so many errors that were happening because I created like 1,500 problems. So, there's definitely a lot of problems in there when you have a lot of creation like that in a very short period of time. So this last homework, it only had one solution, so you weren't given, or this upcoming homework, you were only given one problem. So that's why there is no answer there. So there will not be an answer there till after the due date. So Thursday night after the due date, there'll be answers that will be posted on there. So feel free to reach out to me and give me feedback if you like that better, or you're like, no, I do want, even though there were some errors, I prefer to have lots of practice problems. Okay. All right. Any other questions?
This might just be me needing to look through the Canvas page, but for the homework that's due this week, is there example problems that are like similar anywhere?
No. Nope. They'll just be those. So if you need help on those, you can feel free to reach out to me or to the TAs. So that's the trade-off. Like I wasn't able to give examples where you can be like, oh, let me try it, and then we get like a solution, so now I can understand it and then try another one and go on. So yeah, anyway, give me feedback if you like this or not. I'm happy to go either direction. I just know as myself, that's why I started off with giving a lot of problems, but it did create a lot of errors because I was doing it in a very short amount of time. So, all right. Any other questions, comments? Okay. So, I guess that's two of them. All right, so first topic. Is KCL KVL, so we're gonna pull up some problems that we can work on. All right, so we're gonna grab this one. And again, this is another place you guys can go. This has extra problems, practice problems. So this was the Eulabee's link that I have going to these practice problems. So this one asks for how much power is delivered to device 3. So that would be this location. So go ahead and try to solve this, and then you can put what you think is the answer to power delivered to device 3. So this is also KCL KVL, possibly in this. Yes.
Can you scroll up just like a tiny bit? Question.
Sorry. Thanks. I could see it on here, but yeah, there you go. Sorry about that. Thanks for asking. There we go. Okay, so on this, there's a -10 and a +10. How do you know whether it's a positive or negative? Anyone? Yes.
KCL, the sum of the entry nodes would currents need to be equal to the exit currents.
Okay, so you do have to use KCL for this one. So which direction do you want to assume this is going in?
The 1A and 2A, I guess.
So out of down or up to this node?
Up and to the right.
Okay, so you think it's going this direction?
Yeah.
Okay, so if it's not labeled, you can be like, I don't know, let me guess. So you make a guess, then you solve it, and then you see like, oh, okay, it's this value. If it's going the other way, it will become negative, but you leave the arrow the same way. Okay, so if this is the case, this goes in. I'm going to just call it some arbitrary I. And so if I use summation in as plus and going out as negative, this would be plus I plus 4 minus 1 minus 2. And solve this, I get -1, right? 4 minus 1 minus 2 is -1. So +1, and then I have to take it over to the other side. So it actually is flowing down, which makes more sense. If I have 4 amps coming in, it splits, it's going to go up, out, and then down. But I didn't see that when I made my guess. That's fine. So with it going in this direction, power, it looks like everybody got that part, I times V. And then I see on this that if I have labeled this going up, the top is a minus and the plus is opposite. So this has got to be a negative of the power, right? Because they're going in opposite directions. So I put a negative here, and then this is going to be a minus 1 times 10 to give me a plus 10 volt. Okay, so if it's opposite, so note if opposite, you got to make sure if the voltage is this way and the current is this way, power is going to be a negative I times V. So it will be a negative of that, okay? All right, so we got a plus 10. We'll go back, we'll put this in, and yay, it is correct. Another one. Okay, this one. Okay, so for this circuit, what is the voltage V2 at the indicated node relative to the ground node? So that means what? I'm going to highlight this node and highlight this. And somebody can just say, what is V2 here? It's what? It's going to be 6 volts, right? All of those are in parallel with each other. So this will be 6 volts. Oh. And yes, that would be 6 volts. So that one hopefully was pretty easy to just see right away. Yay, it's correct. All right. Okay, let's see if we can do another one. Dependent. Okay, I can go to chapter 2. Okay, I'm going to use the same circuit. Let me capture it again. All right, so different question for this same circuit. Okay. All right, let's do this one. What is this current I1? And what is this current I2? So find I1 and I2. Right, I'll restart the. Okay, so I look at this and I'm like, I have no idea where to start. So what would you do first? So what I would do first is to always try to label first every current in a branch. So I already have I1, I2 labeled, so I would go here and say, okay, again, I don't know which direction, I'm just gonna arbitrarily choose one. So I could call this I3, and then I'm gonna again do this one and do I3. So now I have I'll do that one I4. Every current in every branch. Then I would want to label voltages across everything. But I do know that I do have some known information. So if I highlight this, I see like, oh, okay, that's all one node. We already did that last time. And from that, I'm like, oh, I already know that all along this top one, I have 6 volts anywhere I measure across the top node. So that means that I have 6 volts across the battery. That also means that I have 6 volts here. I've got 6 volts here. Every one that's in parallel, I've got 6 volts. So I could do a KCL into that node. Oh, I forgot to label this branch, sorry. And there's current also in this branch, so I5. So now I have every current in every branch. And then I've labeled all the voltages across all the elements. And I could do a KCL at the top of there. If I again do current going out is negative, I have negative I4, negative I3, negative I5, plus I2, and a negative I1 equals 0. So I have a lot of unknowns there. I've got 5 current values that are unknown there, so I still need additional values. So then I know, well, I've got Ohm's law. So for every resistor, I have a voltage across it. I can define, so I know each one has 6 volts, so I4 times 2. 6 volts is also equal to I4 times 4. 6 volts is also equal to, so I've been doing positive because you see I labeled the plus the same direction as my currents, but in this one, this current goes up and I have opposite. So with the opposite, I have to do a negative of Ohm's law. So with opposite, again, it will be V is equal to a negative I times R. So in this one, it will be a negative I2 times 2. And then the last one is 6 is equal to I1 times 4. So then this, I'm like, well, I have enough equations and I have all my unknowns, except for I would need to know I1, I2, I3, and I4 in order to solve I5 here. So I1 would be 6 over 4, which is 1.5 amps. And I2 is 6 over 2, which is a negative 3 amps. If I wanted to solve I for I5, I could then do the same thing. I4 is going to be 3 amps. And, oh wait, I wrote that wrong. 6 is I4, and then this was I3. I3 was I3 times 4. So I3 here would be 1.5 amps. So I could solve for I5 if I wanted to in that one. All right, questions about this one? That seemed to stump quite a few people, it seemed like. Yay, nay? Okay. let's do chapter 2. Okay, so let's do this one. Okay, what is the value of I3 here?
6.
Thank you. Yes, good job. So 6 amps comes in. So 6 amps comes in up here, and then it splits. How much is I1? Or give me the equation for I1.
6 times 6 over 2 plus 6.
Yep, 2 plus 6, so 8. So 36 over 8. And I2 will be, what's the equation for that one?
6 times 2.
Correct. Correct. So 12 over 8. And then I3, or wait, we got I3. I4. Yep. And I5. Wait, did I write that right? No. 6 times, sorry, I5. Oh my. Okay. One of those days. I1 is the same as I4 because the resistors are the same, and this is the same for I5. Questions on that? All right, so yep, this is 6. Check, correct, yay. All right. Okay, let's do this one. This will be good. Okay, so it said here to assign this node here as ground, which means this is your reference 0 point. So 0 volts here. So again, solving this, label every current in every branch. So we know 3 amps through the 12 volts. I'm again arbitrarily picking this direction. I'll call it I1. Call this I2. And this I3. What's going through this 6 ohms on the right? This will be 1 amp, I heard somebody say. Correct. So it's the same branch, so that's 1 amp. Same idea here is that that 1 amp goes around the corner and also goes through there. So what is I1 here? So -2, +2. How do you know? Sum the current, correct. So summing that current going in as positive, going out as negative. So 1 minus 3 minus I1 equals 0. So I1 will be a -2. So that's how you know if it's plus or not, or minus. I2 will be what? Correct. I2's got to be 0. If you have 1 amp coming in and 1 amp going out, then it's got to be 0. If you don't see that, again, we can do a plus I2 plus 1 minus 1 going out. And we can see, oops, we can see, yes, that is 0. So what is, oh, and then I3. Okay, again, same idea. Going in is 3, going in is I3, and going out is 1. So I3 will be 2. And if you're not sure the sign, but you're like, oh, it's got to be probably 2 because I have 3 coming in, 1 going out, but you're like, I don't remember if it's plus or minus, just do the summation to get the sign correct. Yes?
Where does I3 have 3 amps coming in?
Ah.
No, that'd be 3.
So this wire here has come from this side, right? It's the same branch. So it's just going to go around the corner, so you have 3 amps coming in. So everywhere,
3 amps plus.
3 minus, 3 goes in, I3 goes in. Oh, you're right. 3 goes in, I3 goes in, minus 1 goes out, so I3 will be minus 2. Thank you, sorry. I'm a little tired. Okay, minus 2. 3 goes in, I3 goes in, and minus 1 goes out. All right. Minus 2 for that one. Okay, so if I2 is 0, what does that mean? What's 4 volt going to be? What value will be there? So there's 0 volts here, right? Because there's no current. If there's 0 volts, and let me go back, and I forgot to put that in, but you can highlight all of the nodes. So between the green and the purple, I have 0 volts. So what will purple wire become? If I was to physically measure this, I put a probe on, a red probe on V4, and I'm comparing it to ground. Thank you. 0 volts. Correct. 0 volts. So if I have 0 volts there, what did it want? Again, determine node voltage V4. Okay, so 0 volts. What if I want to know V1? V1 at a node means that I'm taking, the probe is plus there, and then I'm measuring it to 0 volts. And 0 volts is also on the bottom, so it's also measuring it to this one, which is across which? That means it's across this resistor. So is it a plus or a minus here? Hint. Opposite, so minus 6 times 1, minus 6 volts. Or I could say that it's also the voltage between that node and the green one, which is I1 times 3. And I1 was -2 times 3, so minus 6 volts. Either way would get you to minus 6 volts. What if I was to measure V3? Would be the same idea. V3 could either be the voltage across the 6 ohms, or it could be the voltage across the 3 ohms there. And it will end up being -6. I'll just write it out really quickly. So V3 could also equal 1 times 6 for +6, and then, or V3 is a minus I3 because of the signs are opposite, times 3, and I3 was a -2, -2 times 3 for +6. Okay. All right, any questions on those? Okay. All right, let me find. Okay, let's do this one. Okay, using this circuit, we want to change this to an equivalent resistance and then find the voltage VL. So VL, what's going on here, I guess, first, looking at that. Floating wire. So what does that mean if it's floating? Current.
0 current.
0 current. So with 0 current, what's my voltage across here? 0 volts, correct? So I can pretty much ignore this and say that my voltage VL is the same that's at this node in comparison to this, which is also the voltage across the 2K. So this is also VL. So can I change this resistance to find VL? Hopefully you say like, no, that doesn't look easy. So what could I do here to solve for that?
Sorry, I just have a quick question.
Yeah.
How did you figure that it was 0 volts?
So Ohm's law, V is equal to IR. So if this is 0, voltage has to equal 0. So no matter if you find one or the other, if you find voltage is 0, then you know, well, the current has to be 0 too. There's probably no resistance there. So that's why. So if I wanted to find VL here, what would I do? Do I see that this is a configuration that I can solve for? What does it look like? You only know voltage is a divider, and there's a current source, so it's got to be a current divider. So what would be, how would I solve for VL? Take a minute, think about it. Go ahead and try to solve for VL there. There's a pretty good consensus going on. So 5 volts is correct. So if you find the current in that branch, you can use that VL is I times 2K. And to find the current, you identify that it's a current divider, and that current equation will be 5 milli times 5K over the summation of all of them, which is 10K. So 2.5 milli. So 2.5 times 2K gives me 5 volts. Oops. What if I labeled this, I wanted you to find Vx. What would be the difference to find Vx here? What would be Vx?
I have a question.
Yep.
Where's the 10K coming from?
5K from the opposite branch, and then in the branch itself, so the branch, this branch is, oh, that didn't show up very well. Find a color in here, there we go. This branch is 3K plus 2K.
But isn't it, if we're finding the IL, I guess,
Uh-huh.
then wouldn't the other branch would be the K I K3?
So you have to add all of the resistance in the branch. So in this branch, there's 3 and 2, so this branch is 5K. So that branch is 5K. So this is going to be 5K from the other branch, and then in this branch, it's 3K plus 2K combined.
Got it.
Does that make sense?
Yeah.
Okay. So note that Vx is the same idea, except for the current is going opposite this, right? So this is going to be plus to minus, and those signs are opposite. So you're going to get a negative Ix times 5K. Label that Ix, and Ix is the same idea. It comes in from the 5 milli. Opposite branch in this case is also 5K over the 10K. So I get 2.5 milli. Sorry. Which is that the 12.5? Times 5, yeah. So 12.5. And it's a negative 12.5 volts. So same idea, just that you have the current is labeled, or the current flow. If I put it up, I could do that, but then I would find it be a negative Ix. So because those are opposite, I have to do a negative I times R. All right, questions on this one? Let's see, transformation. All right, find the equivalent resistance. Between this node and this node is A to B. So ignore the current. And instead find our equivalent there. Okay, so find our equivalent. Okay, a couple people answered. So what's in parallel here? And what's in series? Anybody want to say? What about the 10 and the 10? Okay, good. So parallel. So I've got, I'll come back to that. What about the 40 and the 20? That's a different branch. Yep, series, correct. And then at this node, I don't have anything kind of in parallel, but I noticed that with 25 combined with this one, that those would be in parallel to the 40 plus 20. So here I could say that this is 40 plus 20 in parallel with so 40 plus 20 in parallel with the 25 plus 10 ohms in parallel with 10. And if I combine those, then I'm going to have a pathway from A back to B, and so this would just have an addition of 5. So 60 in parallel with 25 plus 1 over 10 plus 1 over 10 is 5. So 60 plus 5, and so this is 1 over 60. This ends up being 5, so this is 1 over 30 plus 5, and that ends up being 20 plus 5 for 25 ohms, which was correct for you guys that put it in there. All right, any questions on this? Okay. So, let's see, equivalent. Okay, so let's do the Thevenin of this one. So we'll also give practice on some other ones. So go ahead and find RTH for this one. And then also go ahead and find VTH. Some differing answers. Okay, everybody is kind of coming to an agreement on this, so at least those that are responded. So as far as the Thevenin resistance, it is 5.4 ohms. So A and B, I'm going to open up the current source. So redrawing this gives me the following circuit. So I open this. And then my pathway, let me highlight these. Everything in this is one branch, so do a different color. So all of those are going to be in series. Blue go. So I could kind of combine these as one element, so 6 ohms. And then hopefully you can see that 6 is in parallel with 4. And so the R equivalent, which is your RTH, put RTH here, is going to be 3 plus 4 in parallel with 6. So 3 plus 1 over 4 plus 1 over 6, which gives me 5.4 ohms. For the voltage VTH, there's 0 volts here, 0 current. So how can I find VTH?
The voltage across the form.
Correct. So the voltage here, and so I could call this I1, and with no current going through the 3 ohm, this is also I1. So VTH is I1, and it's the same plus or minus with the direction that I labeled I1, so it's going to be a plus I1 times 4. And I1 is a current divider between the 4 ohm and then the 4 plus 2 plus 4, 6. So I1 is 12 over 10. And so this is 4 times 12 over 10, which is 4.8 volts. Oh, what's that? Okay, let's see. So we're kind of out of time. I didn't get a chance to do a couple of the problems. So problems I weren't able to get to for this review was the voltage law, voltage dividers, Wheatstone bridge, superposition, and max power transfer. Oh, let me go. I can do one with max power transfer. Okay, so with this solution for your Thevenin here, what if I was to put a resistor RL here, what value of RL do I want to use to be able to give it max power? What value? $5.4, thank you. So it's going to be your Thevenin value of 5.4 ohms. Yes?
Like max power, like always that?
It's always going to be that.
Yeah. It's not like normal.
Yep, it's always going to be the RN, which is your RTH. RN always equals RTH.
Okay.
Yep, so your max power resistor value will be equal to your Thevenin resistor value. All right, see you guys on Thursday.